Hey guys, this is Dr. Duncan with a supplemental video to help you understand the use of zero no-growth isoclines to better understand how interspecific competition shapes species interactions. Let's start with some visualizations that help us see how competition plays out between two species. Because birds are definitely the most superior group of animals on the planet, let's explore competitive outcomes via these two guys, the chicken and the greenfinch. First, I want to illustrate some simple aspects of competition theory. Let's say that an ecosystem can support a carrying capacity of 24 chickens and 24 greenfinches when it's at equilibrium. You got 12 individuals of the greenfinches and 12 individuals of the chickens, even though both of which have a carrying capacity of 24. The chickens are unable to reach their carrying capacity because the greenfinches are consuming resources that would otherwise support chickens, and the reverse is true as well. But if feather hunters begin coming into the ecosystem and killing greenfinches, then there's going to be more room in the ecosystem for chickens. When greenfinches die, chicken populations can grow larger and reach closer to their carrying capacity. Now, the reality is that many different factors can shape competitive outcomes between two or more species. Carrying capacity is important, but because numbers matter in the game of resource acquisition. Recall that carrying capacity is influenced by many other factors in the ecosystem, including some of these listed here. Carrying capacity is also influenced by competition, but for the purposes of studying competitive outcomes, it helps to consider competition in its own category and leave all those other factors to influence carrying capacity. So what factors influence the strength of those competitive interactions? Well, think back to what you've learned about the types of interspecific competitive interactions. There's consumptive competition, territorial competition, overgrowth competition, etc. In short, there are many ways in which traits of the species can help or hinder its ability to compete with a competitor. Now, the combined impact of one species on the other can actually be measured, and that quantification is known as alpha, where alpha 1,2 is the competitive impact of species 2 on species 1, and alpha 2,1 is the competitive impact of species 1 on species 2. Okay, let's review the three possible outcomes when two species compete over resources. The first is stable coexistence, where the impact of each species on the other isn't enough to completely push the other species out of the ecosystem. Let's start with an ecosystem where there's one greenfinch and one chicken. Both populations are well below their carrying capacity, so they're going to grow. Eventually, they get to the point where there's no more available resources and both populations are maxed out. Neither one reaches their carrying capacity because the other is present and using resources each could use. But each species has other resources that it can use in the environment, so the competition doesn't eliminate them. For example, the greenfinches and the chickens both compete for pancakes, but greenfinches can also eat muffins and chickens don't. Therefore, the greenfinches are still able to survive. Okay, the second set of competitive outcomes is the one where one species has an advantage over the other, and it always wins in a competitive match with the other species. So let's imagine that the greenfinches and the chickens both rely heavily on the same food type. But let's say those greenfinches have an advantage over the chickens because they reproduce faster and or because greenfinches are smaller and need less food per each individual. So as time goes by, both populations grow, but the greenfinches grow faster. Soon the environment is saturated with both species, but the greenfinches still have an advantage here, because every time a chicken dies, it can be replaced by several greenfinches. But every time a greenfinch dies, it can only be replaced by a greenfinch. Thus, greenfinches hold on to their resources in this competitive matchup, and they can only gain more resources over time. Eventually, greenfinches squeeze out the chickens from the ecosystem entirely. The third and final set of outcomes is that the situation when one species or the other can win. It can go either way. Now this is when two species are similar enough that the results of their competitive outcome depend on the numbers of both species. It's important to note that there can be competitive pairings where one species that wins most of the time, but there are other times when the other species can also win. So in short, it can go either way. Now to visualize this, consider a situation where both greenfinches and chickens have a big impact on each other, but depending on the starting sizes of the populations or other factors, the outcome can go either way. Here we start with more chickens than greenfinches. As both populations grow, the size of the population has a lot to do with the initial starting size. In this case, chickens have an advantage, and ultimately, they take over. Had greenfinches started with more individuals, then the greenfinches would have won instead. Now, we can illustrate these outcomes from these competitive interactions quantitatively, so with numbers, using our carrying capacities, our alphas, and the use of these zero no-growth isoclines. So let's look first at how to construct one of these graphs. First of all, we see that we put species 1 on the x-axis. That's always the case. We will always do that. So here's species 1 here. And we will always put species 2 on the y-axis, the vertical axis. That will always go on the vertical axis. Now the graph here, this space, is actually the numbers of both populations plotted against one another. So up here in this zone of the graph, you would have high numbers of species number 1 and high numbers of species number 2, for example. Down here at the bottom left, we have relatively low numbers of species 2 and low numbers of species number 1. Okay, so now I've put on to our graph space here what's called an isocline. This is our zero no-growth isocline. It basically represents the places in this graph where the population growth is 0 for species 1. We're going to later do one of these for species 2, but right now we're just starting with species number 1. So at any point along this blue line, our ZNGI, for species 1, the ratio of the two species would result in 0 growth for the population of species number 1. In other words, anywhere along that line, species 1 cannot grow anymore because species 2 is using up too many resources. For example, down here near K1, where you've got a lot of species 1 but very few of species 2, along that line, species number 1 would go to its carrying capacity if the final members of species number 2 die off. And it would wind up converging on K1 right here, okay? But along that blue line, you wouldn't have any growth of population number 1. Alternatively, here in the middle of the line, we have relatively equal numbers of the two species, but population 1 is still not going to be able to grow if that exact ratio of species 1 to 2 is right there along that line, on the ZNGI. And of course, the farther up and to the left we go, up here, you're having higher and higher numbers of species number 2 and smaller numbers of species number 1, but still, along that blue line, there would be no growth for species number 1. Okay, so now let's represent the space around this isocline with arrows that indicate the direction of the population growth for species number 1. These arrows are showing growth for species 1 in the spaces to the left of the isocline and in the space to the right of the isocline. Notice that all the arrows are horizontal. That's because they're aligned to the x-axis, the horizontal axis, because it's that x-axis that shows growth of the growth or decline of species number 1. To the left of this line, we see that we're in a zone of positive growth for species number 1. So there's enough resources that the population grows, and so it's relative to the x-axis, it's moving over and to the right. On the other side of this line, to the far right, we're in negative growth territory for species number 1. Species 1 is, the population size is too large relative to the resources that are available, and so that's going to pull the population to the left to reduce in size. Okay, so far so good, but this ZNGI alone doesn't show us who wins in competition between the two species. For that, we need an isocline for species number 2. So here's the isocline for species number 2. It's basically the same graph and it functions the same way, but instead, notice that the carrying capacity for the species we're looking at here is on the vertical axis. This is the carrying capacity for species number 2, and species number 2's carrying capacity divided by the alpha 2,1 is down here on the x-axis. Okay, so this is the opposite of what we saw in the previous. So here we see the direction of population growth for species number 2 in graph space. Above this line, there are too many individuals of species number 2, and so therefore its population is going to go down, no matter where it is in the graph space above this line. Below the line, the numbers of individuals of species number 2 are small enough that the population is going to grow. So relative to the vertical axis, the population is going to grow. And just to reiterate one more time, the line here, the ZNGI, and I'm going to draw a parallel green line just to draw your attention to it, along that red line, the numbers, when you plot out the numbers of species 2 versus species 1, at any of those positions on the red line, you're going to have 0 growth for species number 2, whether it's there, or it's up here, or it's down below here. That's just the zone in which there is no growth, either positive or negative, for species number 2. That's why it's called the zero no growth isocline. So now that we have our ZNGIs for both species, we can combine them to see what happens in the competitive interaction. So here's the scenario in which species number 1 wins. Note that the ZNGIs are parallel to one another, and species 1's ZNGI, represented here with the blue line, is the outermost one. It's on the outside of the two relative to the origin down here at the lower right. That tells you up front, you already know that species number 1 is going to be the winner in that situation. Okay, what you now see on the graph is what's called a vector sum diagram. And here it is at the lower left. All right. So what's up with these crazy arrows? In each case, these arrows show the population growth for both species 1 and species 2. Here in this space in the lower left-hand corner of our graph, we're in the zone of positive growth for species number 1. That's why we have a blue arrow here that's moving over into the right relative to the horizontal or x-axis. It's positive. We're in positive growth territory for species number 1. Similarly, we're in positive growth territory for species number 2, represented by the red arrow, because in both cases we're below the ZNGIs for each species, and so you know that we're in positive growth territory. Now, to understand how these vector sum diagrams work, I want you to imagine that species 1, our blue species here, is growing and pushing to the right, like physically pushing to the right on the graph. Meanwhile, species 2 is also growing and it's pushing upwards. So it's pushing up to the relative to the vertical axis. And it's this combination of pushing to the right and pushing upwards that sends the combined populations of both species up and to the right. And so that's represented here by this dotted green line. And all this is to say that when the two species are plotted together and they wind up in this triangle here at the lower left-hand side of the graph, the combined trajectory for the two is always going to be up and to the right. And of course, ultimately, what's going to happen? It's going to wind up crossing over that ZNGI and into this next zone. But we'll get to that in just a moment. Let's look first at the graph space here at the upper right-hand side. You see that the new vector sum diagram has appeared. And this is indicating that Species 1 is in negative growth territory. That's why its arrow is pointing to the left. It is up and beyond its ZNGI here, the blue line. And the same is true for species number 2. It's in negative growth territory for species 2. It is way past the red line over here, the ZNGI for species number 2. So the combination of species 1 declining and species 2 declining is going to lead to the combined movement of our point on the graph, which represents both species. It's going to lead to that combined movement down and to the left. And of course, that's going to approach our first isocline that it will encounter is our isocline for species number 1. So anywhere in the space to the right of the blue ZNGI for species 1, the force is going to move these two species down into the left. Okay, so as you've probably already anticipated, it's the middle zone between the ZNGIs that's going to show us which species is going to win in this outcome. And in this zone, we see that we're in positive growth territory for species number 1. You see the blue arrow here pointing to the right, positive growth because it's below the blue ZNGI. And we're in negative territory for species number 2. So species number 2 in this situation is going to decline, while species number 1 is increasing. That means any time that the two populations graph out into this zone here, species 1 is going to be winning. So ultimately, if the two populations graph into this middle zone, the trajectory is going to pull them down to the right, ultimately winding up at this situation, which is right here at the carrying capacity for species number 1. Species number 2 will go extinct in this ecosystem, and species number 1 will prevail, and it will have all the resources to itself. Now, the opposite would happen if you look at the far right. The opposite would happen in this situation where species 2 has its isocline as the outer isocline, and that means that species 2 is going to win, and all the trajectories in the graph ultimately are going to lead to species 2 winning and reaching its carrying capacity. So trajectories will lead into the middle zone from either the lower left or the upper right, and within the middle zone they wind up leading up and to the left and towards the carrying capacity. Okay, so there you have it. These are the two outcomes where one species wins all the time. Sometimes it's species 1, as we see on the left, and sometimes it's species 2, as we see on the right. Now sometimes, as we saw with the greenfinch and the chickens, you can have a situation where both species have advantages over each other, and the outcome depends in part on the size of the two populations. We can see this here where the two ZNGIs cross, and importantly, notice that the K1 down here at the lower right and the K2 up here at the lower left are on the outside of both the X and the Y axes relative to the fraction of the K divided by alpha. Okay, that tells you that in these situations where you've got this arrangement on both axes, you're going to have a condition where one species or the other will win, and it depends on the numbers and the populations of the two species. Okay, now you see that the vector sum diagrams have appeared. Two of them are very similar to what we saw before, the one in the lower left and the one in the lower right. But what is different are the two vector sum diagrams that are in these sandwiched zones of the graph that are in the middle. What is different is that middle zone of the graph, you have one triangle up here to the right where the combination of population sizes is going to lead to species number 2 winning, so it's going to go up and to the right and wind up here at K2, as I'm illustrating on the graph here on the y-axis. Or if you're in this triangle down to the right, the combination of the two populations is going to lead to a trajectory leading down here to K1, where species 1 wins. Okay, so this is the same graph as we were just looking at, but now what I've done is I've drawn a green line from the origin down here at the lower left up and through the intersection of these two lines here and then up to the right. And all of this is to show that this zone that's to the left and above the green dotted line is the zone of the graph where the combinations of population sizes for species 1 and species 2 are going to lead to species 2 winning. No matter what happens, species 2 is going to win. All right? This is what happens in this zone to the left of the green line. To the right of the green line, we're going to have situations where it's going to lead to species number 1 winning. And you can figure out that by running this line from the origin here through the intersection. Whoa, I don't know where that line came on. Hang on. Sorry, I had to clean up that glitch that popped up there. What I'm trying to illustrate here is that you draw that line from the origin here at the lower left through the intersection and then run that line out. And that shows you to the left of, and above that line is the zone of these competitive outcomes in which species number 2 will win and reach its carrying capacity, and to the right and below the line you wind up with a situation where species number 1 wins and it reaches its carrying capacity. Okay, one more thing I want to show you about this. If you look now to the upper right, there it is, now that's appeared. At the upper right, it's the same setup as before. It's one of these who wins situations where it can go either way. But I've aligned the isoclines a little differently, especially the blue one here. You'll notice that I've moved the K1 for species 1 to the left a good bit. Basically to change the orientation of that green line and to change the amount of space that in which species 1 can win. And all of this to illustrate that you can have different scenarios where it can go either way. But in a situation like this, species 1 is at a big disadvantage. You'll notice that you would have to have a situation where there's a lot of species 1. So this is this zone here, a lot of species 1 and very few of species 2 in order for species number 1 to be the winner. Meanwhile, on the other side of the green dotted line, there is lots of possible combinations of the two species where it is all going to lead to species number 2 going to win. In this situation up here and to the right, we're seeing how species 2 has some big advantage over species 1. It can't win all the time, but it wins most of the time. Okay, finally we get to the situation where both species compete with one another, but the competitive impact of each species on the other is relatively weak, and neither species can cause the other to disappear. Notice that the carrying capacities for each species relative to the carrying capacity of the other species divided by alpha is on the inside of the curve, closer to the origin, which of course is down here, this being the origin that I'm circling now. And again, we see on the x-axis how the carrying capacity is to the left of this fraction here, which is K2 divided by alpha 2,1. When you see a situation like that, where the curves cross and they intersect somewhere in the middle, and the carrying capacities are on the inside, closer to the origin, in those situations, you're going to get coexistence of the two species. Now, when we look at the vector sum diagrams for all of this graph space, we see the usual situation in the lower left where the push between the two, from the two populations is up and to the right, and we see the usual situation in the graph space up and to the right where the combined push of the two populations is down and to the left. And in the middle zone between them, instead of the combined push being out towards the carrying capacities, instead the combined push is towards the center of the graph. So this is a situation that leads to coexistence, where no matter what ratio of species 1 to species 2 you start with, it will always lead to this stable equilibrium here in the middle where these two lines intersect with one another. Okay, this is the same graph. I just did a little tidying up there to get all my notations out of the way to show you one last thing. And that is that when in these coexistence situations, if you want to figure out like how many individuals of species 1 can exist in this coexistence situation and how many individuals number species 2 can exist, all you have to do is plot straight down from the intersection of those lines to the x-axis, and this number here, whatever that number would be, and of course we don't have numbers on our graph, whatever that number would be the number of individuals of species 1 that would exist at coexistence. And over here on the left, this would represent the number of individuals of species 2 that would be around at that stable coexistence situation, that stable equilibrium. Okay, so that's a wrap. I hope that helps. Again, this is one of my first screencasts, so there are a few glitches here and there, and I apologize for that. Just remember that if understanding of this is complicated, if you're having trouble, reach out to your instructor, and we're going to be there for you to help walk you through this and find a way for you to understand.